Today we'll look at Cauchy sequences. We won't cover them too much. We won't cover too much today. We'll restrict it to things that I think are reasonable, and you can review. We'll review some material that we have covered so far about what would be important on the exams. For example, so Cauchy sequences. Okay, 3.8. Oops. Definition. A sequence Pn in a metric space X. I'm going to ignore the metric space part because that is going to be our standard thing. A sequence, actually it is important in this case, sequence Pn in a metric space X, metric space X is said to be Cauchy, is said to be Cauchy if Cauchy is a Cauchy sequence if for every epsilon greater than 0 there exists n in positive integers n such that distance of Pm, Pn is smaller than epsilon for every n, m greater than capital N. Okay? Which is to say that given there exists an n greater than 0 such that any 2 points after capital N are going to lie within a small distance of each other. Okay, let me define another thing. Definition: the diameter of a set, let E be a subset of X, let E subset of X, non-empty, and let S is equal to set of all real numbers, set of real numbers dpq such that actually dpq such that P and Q belong to E. Okay? Then the supremum of S, is called the diameter of E, is called the diameter of E. Okay? Note, diameter of an interval is simply the length of the interval, is the length of the interval. Okay? Now, if Pn is a sequence which converges, first, this is a note about diameter. Second, if Pn is a convergent sequence in X, Pn is a convergent sequence in X, then and En consists of points Pn plus 1, Pn plus 2. Sorry, this doesn't. the convergence sequence is a theorem, so I will not write that as a note. If Pn is a sequence in X and En consists of points Pn blah 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 blah, then Pn is a Cauchy sequence. Pn is Cauchy if and only if the limit of diameter, limit n goes to infinity, diameter of En is equal to 0, right? So there should be some point after which the diameters are less than epsilon. So any 2 points in that set should be within epsilon distance of each other. Okay. So now, before we show that every convergent sequence has to be Cauchy, we need some setup for it, which is what I was going to just write down as a note, and then I realized it needs proof, and it is a proper theorem. So to prove it, we need some setup. Theorem 3.10, part A. If E bar is the closure of E bar closure of E, which is a subset of X, then diameter of E bar is equal to diameter of E. Di. Diameter of E bar is equal to diameter of E. Okay? And part 2, if Kn is a sequence of compact sets, if Kn is a sequence of compact sets, in X such that Kn contains Kn plus 1, and if actually their diameter is going to 0, diameter of Kn is going to 0, then we know that from before that, oh, such the intersection of these is non-empty, then intersection n is equal to 1 to infinity Kn is not empty, but in fact it consists of exactly 1 point. Consists of exactly 1 point. Okay. Proof of part B is really trivial. I won't leave that. I will just mention it. Part A. Well, it is clear that diameter as E is a subset of E bar. E belongs to E bar. It is clear that diameter of, I don't need hence. As E belongs to E bar, diameter of E has to be smaller than or equal to diameter of E bar, right? As we are looking at the supremum. So now to show that diameter of E is greater than or equal to diameter of E bar, or we have to show that they are strictly equal, fix epsilon greater than 0. Okay? Choose P comma Q belong to E bar such that and choose P comma Q belonging to E bar. Then there exist points P comma Q P prime comma Q prime in E such that distance of P comma P prime is smaller than epsilon and distance of Q comma Q prime is smaller than epsilon. Okay? Therefore, distance of P comma Q is smaller than or equal to distance of p comma p prime plus distance of q comma q prime plus distance of p prime comma q prime, and this is smaller than or equal to, well, what is the maximum value of p prime comma q prime? It is diameter of e. And what is the maximum value of distance of p comma p prime q comma q prime? It is each epsilon. So distance of p comma q is smaller than distance of is smaller than diameter of e plus 2 epsilon, not epsilon, 2 epsilon, right? Therefore, diameter of e bar is smaller than or equal to diameter of e plus 2 epsilon for every epsilon greater than 0. And the only way that can happen is if diameter of e is smaller than or equal to diameter of e bar is smaller than or equal to diameter of e, and therefore they are equal. Therefore, diameter of e is equal to diameter of e bar is equal to diameter of e. That proves part A. For part B, we know from before, we know intersection n is equal to 1 to infinity, kn is non-empty, right? Because intersections of compact sets, if you go down, as long as their finite intersection is non-empty, their infinite intersection is also non-empty. This was theorem 2.36, I think. Okay. Then now, if intersection n is equal to 1 to infinity kn contains more than one point, then the intersection is non-zero. That's right. And then the diameter is non-zero. Then diameter of k is greater than 0. Then diameter of k is greater than 0. Okay. And therefore, let us call it some delta, which is greater than 0, right? Therefore, well, diameter of kn is greater than delta for every n. And contradicting limit n goes to infinity kn, diameter of kn is equal to 0. Okay? So, now that we have this, we can show that every convergent sequence is Cauchy. Theorem 3.11. Okay. In any metric space X, X, every convergent sequence is a Cauchy sequence. Part B. If X is a metric space and if X is a compact metric space, if X is a compact metric space, and if Pn is Cauchy, then Pn converges, and Pn Cauchy sequence in X, then Pn converges in X. And part C, in RK, every Cauchy sequence converges. In RK, every Cauchy sequence converges. Okay. Now, it might seem slightly what do you call redundant to have a definition of a Cauchy sequence when you have a convergent sequence, because if everything after an n is with an epsilon ball, then it should converge, right? And the small problem is not necessarily, because the limit point might not be in X. Okay, so the difference between Cauchy and convergent is the limit point explicitly being in X. Is the limit point explicitly being involved. Okay. If maybe I'll introduce it as it comes up. Okay. For now, let's just prove this theorem. Proof. Part A. This is really easy. If Pn converges to P, then there exists for every epsilon greater than 0, there exists an n in N such that for every such that n greater than or equal to n implies distance of Pn comma P is smaller than epsilon over 2. Okay. Therefore, n comma n greater than or equal to m imply distance of Pn comma Pm is smaller than or equal to distance of Pn comma P plus Pm distance of Pm comma P, which is smaller than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Okay? Therefore, Pn is Cauchy. Therefore, Pn is Cauchy. Okay, great. We showed that it's Cauchy. Second, suppose it is Cauchy, then we want to show if my space is closed. Compact, then it's convergent. So let Pn be a Cauchy sequence in compact space X. Be a Cauchy sequence in compact space X. Okay. Then let En is equal to set of points P1, Pn such that n greater than or equal to n. Okay. Then because my sequence is Cauchy, then limit n goes to infinity. Diameter of En bar is equal to 0 by the previous theorem. Okay. Now, En bar is closed subset. En bar is a closed subset of X and therefore compact. Therefore, En bar is compact for every n. Okay. And we also know that En contains En plus 1. Therefore, En bar contains En bar, En plus 1 bar. Okay. Therefore, by the previous theorem, by theorem 3.10b, there is a unique point P which lies in every En. There exists unique P belonging to E, P belonging to X, not E, such that P belongs to En for every n. Okay? Or En bar, actually, not En. I can't say it belongs to every En. Okay? Now suppose let epsilon greater than 0. Okay? Then y3, because diameter of En bar is going to 0, there exists some integer n naught belonging to n such that diameter of En bar is smaller than epsilon for every n greater than or equal to n naught. Okay? Since P belongs to En bar for every n, it follows that distance P comma Q is smaller than or equal to, strictly smaller than epsilon, not smaller than or equal to epsilon, for every Q belonging to En bar. For every Q belonging to En bar, if n is greater than or equal to n naught. For n greater than or equal to n naught. Okay? Therefore, that means Q belongs to En. No, sorry. Therefore, distance of P comma Q is smaller than epsilon for every Q belonging to En. Sorry, I read that wrong and confused myself for a second. Okay. Therefore, if this is happening, in other words, distance of P comma Pn is smaller than epsilon for every n greater than or equal to n naught. Right? Which means Pn converges to P. Okay. Part 3 is really easy. Part C. Suppose xn be a Cauchy let xn be a Cauchy sequence, be a Cauchy sequence in Rk. Then if we show that there is some compact set which covers xn, we are done. Right? By part B. So define En as before. Okay. For xi. Then for some n, diameter of En is smaller than or equal to 1. Then there exists and not in n such that diameter of En is strictly smaller than 1 for every n greater than or equal to n naught. Therefore, the range of xn is bounded. The range of xn is union of En and a finite set and the En naught and the finite set x1 to xn minus 1. Xn naught minus 1. Okay, and hence it's bounded. Therefore, xn is bounded. If it is bounded, then I can take it as a subset of some compact set. Since xn is bounded, it is a subset of well, I can just take its closure. Its closure is compact in Rk. Okay? And now C follows from B. Now C follows from B. Okay? Definition: a metric space in which every Cauchy sequence converges is said to be complete. Every Cauchy sequence is converges is said to be complete. Therefore, corollary: all compact metric spaces and R to the k is complete for every k. Okay? An example: Q is not complete. complete. Okay. For example, take a sequence of rationals. Take a sequence of rationals converging, converging, converge, converg, converging to root 2 in reals. Then the sequence, uh, is Cauchy, but not convergent in Q. Okay. So Q is not complete. Okay. Definition. A sequence of real numbers is said to be a sequence of real numbers is Sn. Sn is said to be, well, first, monotonically increasing, if Sn is smaller than or equal to Sn plus 1 for every n. Or it is called monotonically decreasing. Decreasing if Sn is greater than or equal to Sn plus 1 for every n. Okay? It is said to be monotonic if it's either monotonically increasing or monotonically decreasing. So, theorem 3.14. Suppose Sn is monotonic. Suppose Sn is monotonic. I'm not saying it is increasing or decreasing. It could be either. If it is monotonic, then Sn converges. If and only if Sn is bounded. Proof. We are not going to show that if it is convergent, it is bounded. This way is standard, or is obvious. Is obvious. We have done this before. We have shown the proof using En and showing that, oh, if it is convergent, then the diameter is going to 0. Take things where it is less than 1, and then showing that it is bounded. So we are only going to show that if it is bounded, then it's convergent. So, without loss of generality, since the proof is going to be exactly similar, assume Sn smaller than or equal to Sn plus 1 for every n. Okay? So assume that it's monotonically increasing. Doesn't matter if it's decreasing, the proof goes the same way. Let E be the range of Sn. If Sn is bounded, then let S be the least upper bound of E. If if Sn is bounded, then let S be the least upper bound of E. Let S be the supremum of E, or least upper bound of E. Okay. Then that means that Sn is smaller than or equal to S for every n. Okay. And and for every epsilon greater than 0, there exists an n such that S minus epsilon is smaller than or equal to, is strictly smaller than Sn is smaller than S, smaller than or equal to S. Okay. Otherwise, Sn minus epsilon would be a lower upper bound. Otherwise, S minus epsilon is a lower upper bound. Well, this means that Sn, therefore, Sn converges to S. Therefore, the distance of Sn, comma S is smaller than epsilon for every oops, this should be a small n. For every n greater than capital N, greater than or equal to capital N, as Sn is increasing. Okay. This looks like a delta, which is smaller than or equal to S. This should be an S, not an epsilon. Okay. Therefore, Sn converges to S. Okay. Let us stop this video here. I will upload another video entailing what are the important concepts that you should know / review. Okay, for the exam.